All right, the first of Newton's laws deals with inertia, and this will not take too long for us to get through and go through this. We're just going to answer the questions of what's Newton's first law of motion. We're going to answer the question, how can we analyze motion with the first law in mind? And we've got a handful of vocabulary terms that you might come across: inertia, force, net force, equilibrium, and friction. All right. Not going to get too far into the history of our thoughts on this stuff, but in the 1500s, one of the first scientists to kind of think about this was Galileo. He had some experiments where he was rolling spheres, these balls, down a kind of a ramp, and they had been waxed to reduce and minimize the amount of friction that was going to be on them. And what he found was that when he rolled the ball from the left side to the right, that it almost went all the way back up to the top on the other side. The less friction, the closer it got to going back to the top. And even if he lengthened the ramp, it would still go back to the same height. And so his thought experiment was that if it rolled down to the bottom and it didn't have a height to go back up to at all, that it would just roll forever. And so he inferred that a force isn't actually needed for movement to occur. So we don't really need a force to continue motion. You might need force to begin a motion, but if an object already is in motion, that it may continue indefinitely without friction. In the 1600s, Newton comes along and he used this idea of inertia in his first law of motion. So if we look at Newton's first law of motion, it's also thought of as a law of inertia. It simply says an object with no net force acting on it remains at rest or in uniform motion. In other words, it's going to be straight line with constant speed. So if there's no net force acting on an object, that object's going to continue doing whatever it's doing. If it's at rest, it'll stay at rest. But also, more importantly, if it's in motion, it will continue the motion that it's in if there's no net forces acting on it. As we go through discussing these and throughout the rest of this unit, some of the terms we need is a force, which can be defined as any kind of push or pull. The net force is the sum of all the forces acting on an object. Typically, an object doesn't just have one force acting on it. There's multiple forces. And so when we look at what's going to happen to an object, we want to take into consideration the net force, all of the forces that are going to be acting on it. Oftentimes when things are moving along a surface, we discuss friction, or we say to ignore friction. But friction is the force that's going to resist the motion between two surfaces that are in contact with each other. Inertia can simply be thought of as a property of matter that resists a change in motion. And we can sometimes use the word equilibrium as well. You see the root there of being equal. That's going to be when our forces are balanced. So that's when we have a net force of 0. So there may be forces acting upon it, but if they all cancel each other out in equal and opposite ways, then that object would be at equilibrium, and it would continue doing whatever it was doing in terms of its motion. One of the key takeaways with inertia is the amount of inertia that an object has is going to be proportional to the mass of that object. So the more mass an object has, the more inertia it is going to have. In other words, it's going to have a greater tendency to continue its motion. It's going to take a greater force to change the motion that it's already in. So if you have an object that's more massive, it's going to have more inertia, and it's going to be more resistance to changing its motion, whether it's moving or not moving. Right. Again, an object at rest stays at rest. An object in motion is going to stay in motion. And the more inertia it has, the harder it is to change the motion that it does have. So a couple of video examples. We experience inertia all the time. One of the easiest ways to think about it is in a car, because our car is constantly accelerating, and our body, being in that car, wants to resist whatever change of motion the car is actually having. This first video, you can see, so one of these, don't try this at home, but there's someone riding in the back of this truck, and they're throwing a medicine ball up in the air as they're moving. So you can see as they go through and do this, that when they throw the ball straight up, the ball wants to continue its motion as if it's still part of the car. So when the ball is in motion in the truck, it wants to continue the motion that it has, even if you throw it up into the air. Now, in real life, we've got some air resistance to deal with. So the rest of this video ends up showing that the faster the truck goes, the harder it is for the ball to actually land back in the truck. And if it's a smaller ball that's not, it's more apt to get pushed by the air. Like a tennis ball, it may not end up back in the same place. But with our examples of inertia, we tend to try to ignore air resistance and other types of forces that might be acting on it. The other video here is really quick. There's a couple of pennies on top of a car, actually two cars, and we see one car crash into the other one. And the pennies that are on them want to keep their motion. So the penny that's on this back car was moving forward. It wants to keep moving forward. The penny that's sitting on this front car wants to stay there. And you'll see that even though the car in the front ends up getting pushed, I'll keep the arrow right there. You can see the penny itself just bounces up and comes back down. So that penny is at rest and it wants to stay at rest. The car moves out from under it and it wants to continue being in the position that it was in. And again, the idea, if there's more mass, it's going to be harder to accelerate. There's another little video clip we have right here with this. Again, things that you probably already knew. It's harder to move a desk than it is to move a chair. But if we explain this in terms of inertia, it's simply because the desk has more mass, therefore it has more inertia, therefore it needs a greater force to be able to accelerate it. It has a greater resistance to changing its motion. Additionally, if the chair and the desk were both moving at the same speed, it would take a lot more force to be able to stop the desk as well, because it would have more inertia. It would be heavier and it's harder to change its motion, even if it's regardless of whether it's moving or if it's stopped. So a couple just quick questions, check your understanding. The best measure of an object's inertia would be its what? So in other words, how much inertia an object has. Hopefully we think to fill in this blank is its mass. And the second one says, what net force is needed to keep an object in constant motion? So this is a key phrase here, constant motion. If it's in constant motion, then it's not accelerating. And if it's not accelerating, then there's not a net force acting on it, because the law of inertia is kind of giving us an idea that an object will continue its motion unless a net force acts on it. So the net force needed to keep an object in constant motion is going to be zero. There would be no net force. So there would be forces acting on it, but not necessarily a net force.